Okay, I'm gonna get started. I feel a little lonely here, but I suspect that is at least partially due to the homework being due today, and I expect a couple more people to drift in a little later. So what I'm going to start with is I'm not going to start with discussions of the homework or the project. I'll try to get to that later. But I think I'll start with material and we'll see how far we can get. I'd like to finish up visualization today and hopefully maybe start on another topic, which is modeling. Um, but what have we been doing? We've been looking a little bit at visualization. We've been looking at kind of what are the kinds of plots and things that people use for data visualization. One common plot that people use is a histogram. A histogram is a way of showing if you have the probability distribution of a random variable, okay, or one kind of feature. The x-axis is the value, the y-axis is the frequency. You can represent any kind of a distribution like that by either using a histogram or a cumulative distribution. And usually people like histograms, and histograms are usually good. They're good for showing you where the peak is with a histogram. But if you want to see what's going on at the tail of a distribution, you're generally better off with a cumulative plot. Okay? Any questions about that? No. Hold on. I'm not. Let me see if I'm able to get this to move. Okay. Now, the single biggest advice I have when it comes to histograms is making sure that you have the right number of bins. Okay, here is a figure where we've got a large number, where we have, in this case, a very large number of points. Perhaps it's 100,000. And I'm showing, I guess this was the baseball batting average, if I have to take a guess. So these are numbers that are distributed between, centered around, it's a binomial distribution centered around 0.3. If you plot this with a large number of bins, you see a smooth histogram, okay? Whereas if you only have 100 points, okay, you see a kind of the bell shape. Well, let's take a look at it. Which one of these do we think is best? Okay, if you look at histograms, here we've got data. How many bins do we think is best for the one down below? And I expect unanimous results. Which one do we like?
100.
The one on the left. You like this one?
Oh, wait, the lower one? I like the middle one.
You like the middle one. Okay, so the middle one is, you like the middle one? I think that's probably fair. Certainly having too many bins on a histogram is bad because you're seeing kind of noise and stuff rather than that. When you get a lot of points, a lot of bins is good. What is the rule of thumb concerning histogram sizes and bins? Well, I think you want to make sure that the largest bin has a non-trivial amount of stuff in it. Maybe 1/10 of the total stuff or something like that. That's probably a good rule of thumb. But it should be clear that if your histogram looks lousy, it's because you didn't use the right number of bins. Okay, and that's something I encourage people to remember. Okay, any questions on TV or anything like that? Okay, what I'd like to do is continue on with visualization. Excuse me. Let me come back. Boom, boom, boom. And I'm determined to go through this today, not all my slides, but just the ones that are interesting. What other plots are there that are kind of important plots to know about? One thing that is very popular in science, okay, when you look at science journals and things like that. People seem to love box and whisker plots. What is a box and whisker plot? Well, the individual component is that this is a case where you're showing, it's sort of like a histogram in that, you have discrete units on the x-axis. But on the y-axis, you want to look at not, let's say, the average or the sum, but you'd like to display everything. So what will typically be in a box and whisker plot, the values, the median value is plotted in red, okay? They will then typically show, something like the variance, okay? Namely the width of the box, okay? Or what they will show is, and I think it's more in this case, you will show the median is where the 50th percentile is. They will show you what the 25th percentile is, the 75th percentile as being the size of the box. So the size of the box shows where is most of the data. And the tails, the whiskers, will show the max and the min element. So what's good about a box and whisker plot is that it shows you not only the mean or median value for each one of the bins, okay? But it also shows you what the range of the values are. It shows you what the extreme values are, that's the size of the whisker. It shows you where the bulk of the distribution is, that's the size of the box. Any questions about that kind of thing? Okay, so the good thing is it shows a lot of information. The bad thing is I think something like this often looks like chart junk. If I were drawing, I happen to personally prefer, usually to box and whisker, an array of box and whisker plots like this. I prefer actually contour lines. Show me where the median is. Show me the min and the max. And if you want to show me the other percentiles, okay, like let's say like this. Sorry, hold on. So if you show this, you get the same data as on a box and whisker plot. I personally tend to find that better, okay? But this is up to you guys. Any questions? Box and whisker plots, anything like that? Another kind of plot you see that is useful is what you would call for showing distributions, breakdowns of things. Suppose you have categorical data, time series of categorical data, okay? The x-axis is time, the y-axis is stuff related, is going to be a numerical quantity. Here it's going to be quantities of gun sales, okay? And the claim is that guns fall into a couple of different categories. They can be rifles, pistols, shotguns, revolvers, or other. Okay? So what does the stacked area plot do? It shows as a time how much of each category is sold. Okay? The blue represents how much rifles are sold. The orange tells how much the pistols are sold, and so on. What is informative about one of these stacked area plots? Okay. What is easy to read from a stacked area plot?
Proportional.
Proportional. Okay, one thing I will say that's easy to read is the overall trend of all the things. Okay? So when I look at this thing, the height of the total sum of these areas is the total amount of guns being sold. right? And so my first visual thing when I look at one of these stacked area things is what is the sum, okay? So the good thing is I get a total breakdown of the sum, and I see that this was a good year for gun sales, this year was a bad year for gun sales, and stuff like that. Then for each year, I do get to see the breakdown of sales by type. But how easy is it to read the sales of breakdown by type? So if I take a look at it this way, let's take that year. What was this type of guns that sold the most? Okay. In principle, it would be the color that intersects the line the most. And maybe, I don't know what your impression is with that line. Probably it looks like blue and green and orange are about the same. Okay, and if you have a read better than that. Okay. But it's hard to get at the actual number of sales. Okay, it's hard to get at the trend for any individual thing. If we look at the blues over here, the light blues, what is the trend of the light blues over the time? Light blues were what? Shotguns. Are people buying more or less shotguns over time? I claim that's kind of obscured with with one of these plots, right? You can tell for the blue, the dark blue, that rifle sales have been going up. But I find it's very hard to tell it's easy to tell that the rifles have been going up. But when you look at one of the higher layers on here, the ups and downs are as much a function of the stuff below it than of the stuff itself. Okay? So what's good about that is it does give you a breakdown. You could also call these things stacked, bar charts. You could represent each sale by a bar chart instead of a line area. Which one do people like better? You see how this is the same data where we represent each year by a bar? Here we can connect the bars. Who likes the one version with a lot of bars in it?
Depends on our goal.
What?
It depends on our goal.
Depends upon your goal, okay? Which one? Who likes the bar area, and what is a win for the bar version? Yeah.
I just think it's easier to tell like how big each one actually is.
You think that it's easier to tell for each one of these? Okay, that might be fair. Who likes the one on the bottom, the stacked area version? Nobody liked the stacked area one? I personally happen to like the stacked area one better because I think that there's kind of a perceptual effect here because the white between the bars kind of creates some kind of a pattern you're seeing, and that's what I'm kind of seeing more than I'm seeing the actual data. But this is again to develop your own aesthetic for it. There's another way you could have drawn this data though, would be to use a separate line plot for each type of gun. This is the same data where I drew it, each type of gun got a separate time series that we were drawing. So which do people like better, this or this? And for what reason? What's easier to tell with the lines?
You can see the trend of each individual.
You can see the trend of each individual component. You can see that it looks like shotguns are going out of style. But people are really excited to get pistols, okay? So for understanding components, this is much better. What's lost on this plot versus the other one? Yeah?
So the total number.
The overall trend about gun sales, I think, is lost. So that's kind of what the difference is. This one did a good job of showing the overall trends, okay, while containing the data for the individual ones, but not making it clear. This one, you can carefully understand each one, compare, each of the individual components, but you might lose the big picture.
Can't we add another or sort of another?
And what you're saying is you could add another thing up top that would be total. Now, and that might not be a bad thing, except where would the total line be? If the total line is up here, then that's a great idea, I think. If the total line is up here, note that that is going to shrink all of these things down, and you won't really be able to see them very well. Okay? So, so these are the kind of thinking you would want to think about when you're trying to have data, you want to present it. What is the story you're trying to tell? How much information can you put on one of these plots? The more information, generally the better, unless it starts to overload and confuse your message. Any questions? Okay, good. Here are two stacked bar charts of which are simple graphics showing you basically how many people died on survived and died on the Titanic. Titanic was the famous boat that Leonardo DiCaprio took to the United States. They made a movie. It hit an iceberg. Okay, this shows how many people died and survived the Titanic in each of the three classes. There was the class where Kate Winslet was staying, which was first class. There was the class where Leonardo DiCaprio was staying, which was the lowest class, okay? And you could either show the absolute numbers, or you would show this is a normalized thing, okay? Which one of these plots do people like better? Or better for what reason? What does it show? You like the left one. What do you want on the left?
Because the right, I can't see how many people died.
Okay, so the left one, you like the left one because it shows you how many people died. You can count up the red bars and say 100, 150, 250, another 500. That's something like 750 or so. Okay? So maybe that's one thing that you would see from this. Okay? I like that I can see that there, the number of people in each class. To know, that, what the relative breakdowns are. What is the primary message when you look at the chart on the left? Okay? I mean, what is it that you see when you look on the left?
The third class and
You see that everybody was like Leonardo, most of them were like Leonardo DiCaprio and traveled in the third class, right? What do you see on the right? Okay, when you make it a fraction, make it proportional.
most of them in the third class died.
Yeah, that basically the more money you paid, the more likely you were to survive the crash. Okay? Which is kind of the message of the second plot. Okay? And they're both showing the same data. This shows the more data. You could get the message that a higher fraction of these people in third class died than the first class people. But it's a little less clear. Okay, I think I kind of like this one, find this one more interesting. It's telling more of a richer story, but this one is making clear a different message. Any questions? So stacked bar charts provide a good way to compare distributions, okay, separated into different groups. Okay. Another way to view data that is a very, very useful thing is a data map, okay, or a cartogram. What this is showing us is in the 2012 election when Obama beat Romney. Okay, this is showing us the red and the blue showed us which state voted for which candidate, and the laws of the American election are that all the votes for a state go to the winner of that state. Okay, so this shows us the United States colored by how many, how many electoral votes each state got. It's labeled with how many electoral votes, colored by who the winner was. What is the message of this? If you look at that data map, what do you think you learned from that data map? What does it seem to be telling you? And the people on TV, I'm happy to have people yell out with that too. Anyone see what was the message you see on the first? First of all, who won the election?
Area vote for Romney.
It looks like Romney won the election because there's more red on that map than there is blue, right? So 1%. One thing is that's kind of weird is that the number values are relatively independent of the area of the state. You can have very small, dense states, like New Jersey. That little thing for New Jersey is worth 14 votes. That is more than all of this area. Okay? And so what's good about the cartogram is that the data map here is that it shows the distribution. You start to realize that the Republican areas are the inside, the heartland of the United States. But the coasts tend to vote Democratic, except for the South. The South was pretty solidly red. Okay? So that's a data map. A cartogram is a data map where they distort the area to reflect the variable that you want. Okay? So this on the left looks like the United States. On the right is a map that sort of looks like the United States, right? But each symbol has been shrunk, okay? So that it's basically each place is proportional to its area in real votes. Now, when you look at the cartogram, who won the election? Was it red or was it blue? Blue, okay? And, so a cartogram is kind of an interesting idea. It preserves the connectivity. So you still get the sense that the Northeast was Democratic, the South was Republican, okay? But it does reflect that the area reflects the effect that you want to see. But it does warp the shape of the U.S. Any questions? So which do people like better? The data map or the cartogram? You like the cartogram? Okay. Again, it depends what you're trying to show. I find that if I want to understand, if I want to show who's the winner, this shows me. If I want to understand where it is, if you have a knowledge of the U.S., I still find it hard to find a particular state on this map. It's kind of like the U.S., but not quite like the U.S. Okay? But any reasonable graphics library will have a library for building cartograms. Okay? And it does look like a hard thing to do to preserve area and location as best you can. But there are techniques for doing that, and that's common in a lot of graphics libraries. Any questions? Yeah.
If we want to add another dimension to this, for example, the margin of the win. For example, 49 and 51 has the same result as 30 or 50.
Okay.
30 and 70.
So let's say you wanted to add the margin of win to it. How would you add that thing to that? Does anyone have a proposal? If you wanted to show off what was the winning margin, I would say you play with shading and color, right? You would show something probably about how red is a state, okay? How blue is a state. And the ones that are close probably should be, more neutral colors. You'd like them to still be red or blue, so you can see who won. But you would want to make it clear that that's a lighter thing. We'll talk about color in a little bit, but the effective use of color is important for a good visualization like that. Any questions? So data maps, I think, are great ideas. And data maps apply to things that aren't necessarily geographic data as well. This is one of the great scientific visualizations of all time. What is it? It's the periodic table for chemistry, right? Now, what is it showing? Every block here is one chemical element, and they are grouped according to certain, certain chemical properties that they have. I guess how many electrons are in different shells and things like that. And in this case, they colored every element based on, what grouping of elements there are. I guess there are metals, there are noble gases. These are noble gases in this column. What's interesting about the periodic table is it's a great visualization tool which conveys a lot of information. But it's not it had to be designed rather than, it is not completely a function of nature. Okay? What decisions went on in the minds of the periodic table, which you've all seen? What decisions had to be made in order to make this look so beautiful? Okay? You may think that the periodic table is just chemistry, it's just nature. This is what God did. God developed the periodic table. But there are several places where there are interesting design decisions that kind of had to happen. What are these things down below? Those rows. Does anyone remember? Again, they're called lantide series or actide series.
Each row belongs to one cell.
Does everybody see that this row here really belongs in there? Okay? And this row here really belongs in there. Okay? Why do they take them out? Why don't we leave them where they are? Okay? If we did, what would happen? We could do that by slicing this box incredibly thin, or we could do it by shoving these elements out of the way and then sticking them in, right? There was a certain level of judgment involved in removing this. And that's one of the things that helps preserve, basically our ability to understand and interpret this table. Any questions about that? The basic point is I do think that when you can display data in a visual manner, that's a whole visualization thing. Sometimes there are maps of things, okay? And maps, I think, can be a good thing to do. Any questions about data maps? Okay. And again, you've got access to many tools for building these data visualizations. Some of you grew up using Excel. I always cringe at Excel graphs. I don't think they're very pretty. I don't think they're very sophisticated. Okay? You have access, as you know now, to Matplotlib. You have access to all the visualization libraries in R. Okay? You have enough tools that you have, it's basically limited by creativity. Let's see. Okay, let me not going to talk about this. Okay, what other, let's say, degrees of freedom do you have to be aware of when you're building a visualization? One thing is to use color effectively. That came up when we were talking about how do I encode the margin of victory. not just the what you call it, who won. Okay, so how can we get the idea of a color scale? Typically, we could use color for a couple of reasons. One is to distinguish different classes. You've got Democrats and Republicans. Those are two classes, red and blue. Okay? You could imagine having 5 classes and having a different hue for each block. Now, sometimes though, you're using color as a scale. Okay? And you want it to kind of convey a quantity from lower to higher. And there are different color scales that kind of do a better job of kind of having an ordered perception. If we have black and white, we have what you call it, an obvious scale of brightness from very bright to very dark. And you can, by mixing a fraction of black in with any particular hue, you get a color, okay, that ranges from, the original brightest hue to black. Something like this has an order to it. Saturation is a question of whether you have pure color or gray, okay, and again, you mix it in, there's an order to it. So certain colors, scales, kind of inherently capture an order that you can recognize, bigger to smaller. Certain other color scales, I think, make it harder to capture an order of whether it's, what the linear values are. Many people will use rainbow colors, the rainbow scale, as a natural kind of continuous scale, the spectrum, as a natural continuous scale, okay, to reflect changes. This would be the coldest, the lowest probably, and this would be the hottest or the highest. What do people notice about using the rainbow scale as a color thing? Does it obviously go from hottest to coldest? Okay? It's hard for me to tell. Which do you think is hotter? Yellow or orange? I have a hard time telling myself that, if I'm looking at brightness, it's hard for me to see whether orange is supposed to be a higher value than yellow is. And it's certainly the case that when you look at the spectrum, it's kind of a funny thing. Okay, hold on, sorry. Excuse me, sorry. When you look at the spectrum, one thing that I notice is it looks like green goes on forever. Okay? Where yellow is a very small part of the spectrum. So rainbow scales tell you something about being continuous. But I'm not sure that it completely encodes what you want. If you've got something like the red-blue, what was the margin of victory? I actually prefer a scale where you have blue on one side, very dark blue going to lighter blue. I know this is the wrong color. And red, maybe I'll make this blue. And red on the other side. Now then, 0 is here, neutral is here. You can easily see whether you're above average or below average with that kind of a scale. Any questions? So the color scale is something to think about, okay? And the default rainbow is not always what you want. Any questions? Again, thinking at colors, thinking about colors. If you use colors in the right way, usually your graphic can get can often get easier to understand. One of these was a plot that I encountered some students showed on their thesis exam. And one of them was the plot after I yelled at them and told them to fix it. Which one is better? Okay, which one is which? Let's take a look at this. What is it showing me? This is showing me, it's some kind of study of genes, I guess, or bugs. And he's looking at which genes light up more at night, more in the day, and about the same. So he has a bunch of clusters, and on some cluster, let's say this one over here, this is the proportion of genes that were the same. This is the proportion of genes that lit up at night, and this is the proportion of genes that lit up during the day. Okay? Which one of these cluster visualizations is better? And can you tell the difference?
The second one.
You like the second one. Why do you like the second one?
Because the legend says night and day, so it is obvious that the day should have lighter colors and night should have the darker colors.
Right, exactly right. Because kind of that we do have, again, red and blue have conventions in politics these days. Red and blue and pink, red and blue may have conventions with respect to genders. But certainly we're used to a world where day is when it is light and night is when it is dark. Okay? And so by looking at something like this plot, I claim, is easier to interpret and less hard to misinterpret. Okay? And so when you're not looking to show a continuous scale, but are trying to show classes, it's good if your classes reflect, the colors reflect what classes you are in. Okay? Any questions about that?
The second is the one, the contrast between the same and the nine decrease. So I think it's better to use another color for same.
Okay, you're saying you should use a different color? Well, you might use a different color for same. If I were doing it again, I would probably say, what would be even better here? I would say one thing that would be better is it probably should go day, night, same. If I were looking at this thing, I would probably prefer to have the same, which are the ones that probably are not that interesting. If you put them in the middle, it becomes equal to compare the day and the night ones. And I think that day comes before night. Now you may say, well, night becomes before day, but at least, in my mind, there's kind of an order there, okay? And you could capture it better if we had that. So I would say that you're right. You would want to have a bright sunny color, a dark color. What is the same color? You don't like green? Maybe there's another one. Okay? Any questions? But thinking about, again, what I would like to encourage you is to think about these things. There is something to think about here. Okay? And realize that there are things that are better. Again, we get back to the art notion that I say. Okay? Developing some kind of a language or something like this where we can discuss what we like and don't like about these graphics is kind of an important thing. Okay, what Tufte did as well, again, we talked about, in here about Tufte's main concepts, about the, maximizing data-ink ratio, minimizing lies. Lies are places where people either get the wrong message or they're confused, and eliminating stuff that's just there to decorate it. These are good ideas. One thing that Tufte did that I liked in his book was he had some views of what were the greatest data visualizations of all time. And I think these are kind of interesting to look at. And he also had visions of what were the worst. But let's look at some great data visualizations and see whether we like them. This is a chart from, from Tufte's book, showing Napoleon. Napoleon was this French emperor who made the mistake to attack Russia in the middle of winter. So what is this showing? This is a plot of Napoleon's army, the size of Napoleon's army, as a function of time and space. So what is this showing you? The width of this thing over here is how big was his army when it left Paris. Okay? And it was pretty big, right? And it marches east, okay, to Russia. And it gets smaller and smaller as it gets colder and colder. That's what this is kind of measuring. Okay? And finally, he gets to Moscow, and his army is quite a bit smaller. He conquers Moscow, but as I remember, they kind of burned all the food around there, so nobody had anything to eat. And now he has to retreat, and his army gets smaller and smaller, coming back. That's what the other one is showing. And you see just how few people, what a small fraction of his troops that started that battle, ended up making it home. Okay, it really was quite a, an unbelievable defeat. Okay, and this is kind of showing you troop size as a function of location and as a function of time. Okay, in a way that kind of conveys a lot of what's going on there. Any questions about this battle? This is one of my favorite ones. It's in Tufte's book, okay, also. But this is one that I look forward to every single January in the New York Times. What is this? This is showing me the entire weather of a year in New York City. Okay? What is this showing me? The x-axis here is the date of the year. The y-axis is showing me temperature. And what do I see on the background? I see that the record high, if we take a look at what's being shown here, this is the record high, this is the record low for that date. This is the average high, average low for the date. And the dark band is what's happening in this particular year. And I just find it very, very interesting to look through this thing. Here was a day where, the low temperature that day was higher than the usual high. So that was a very warm day. Okay? You get the size of these things tells you something about how long does a warm spell last compared to cold spells. Does the weather change up and down every day? No, there's some persistence. What is this? That shows me that there was a record that day, record hot temperatures. Okay? Look at this, my God, this was so cold. The highest temperature that day was colder than the usual low. Okay? So this is kind of neat. It shows for every day, 5 temperatures. It shows the rainfall every day. That's what's being captured down here. Okay? In a way that it's quite understandable. Okay, so this to me, a plot is good if I want to look at it. I find myself wanting to look at this every year just to refresh my memory about what the weather was and to view this thing. Any questions or comments? Okay, this is something that is kind of cool. This is a train schedule. Now, you guys have been on trains. Hopefully, you have been on the Long Island Railroad going to and forth between Stony Brook and the city. This is a train schedule between Paris and Lyon, 2 cities in France. And what does this look like? Well, the x-axis is time, And the y-axis is location, right? The train goes from Paris to Lyon, it stops through Tonneray, it stops through Dijon, it stops through Macon, okay? What is each one of these lines? What is this line? Can anyone tell me what that line is? This is a train schedule. What is that thing? Yeah? It's a trade, okay? It shows a trade as it leaves from this station and ends up at Lyon. This is the time it departed. This is the time it arrived, right? Actually, presumably it's presumably started earlier. So this train may appear someplace else. But what's great about, so people see how this train schedule works? Okay? What is great about a schedule like this? Okay? Are there things that you want to know? What are the times that there's trains that are leaving? Well, the ones that are leaving Paris, those are going to be exactly, these are the times when trains are leaving Paris. Does everybody see it? What's the difference between a train that goes from Paris to Lyon and a train that goes to Lyon and Paris? Whether it is has a positive slope or a negative slope, right? Which trains are fastest? The ones that are closest to vertical, right? What other things can you tell? What if you want to get out in a station and have lunch? What's a train that's a good time to get off the train and have lunch? Probably something like this, right? That's a sign that that train was going, and staying there. What is a time when you're supposed to put your hand in the window instead of leave it outside the window? What would be a terrible time to leave your hand outside the window? When you're going to look at something like that, right? You leave your hand outside the window, the other train's going to snap it off, right? And this is something that, something like a lot of these things you couldn't answer on a normal train schedule like the Long Island Railroad gives you. Okay, I find this an interesting way to look at trains. Any questions about that? If people like it or don't like it? One thing that's wrong is that, with this one is that the data grid, the horizontal and vertical lines are probably too heavy, okay? It'd be better if those were lighter, the grid was lighter, okay? Rather than being almost the darkness of the thing itself. Any question? When you have too heavy a grid, they call that imprisoning the data, because it does look like it's in a jail. So, by heavy grid, I mean these horizontal and vertical lines. Okay? Any questions? This is a data map that many of you have probably seen over the last several months, over the last year and a half, I guess, because this has been reprinted many, many times because of the coronavirus epidemic. What is this? This was a famous map that was used to discover the idea of what caused a disease called cholera. Cholera was a big problem in, England, in cities in the 19th century in England, and are still a problem in certain parts of the world. And no one really knew what caused it or how you could fix it. But there was a breakout of cholera, okay, in London. And this gentleman named John Snow wanted to figure out what caused it. He had a data map where he plotted a dot for every person that got cholera, for every house that got cholera. And when he looked at this map, he also showed what was the, what do you call it? Where were there water pumps? Again, back in those days, you didn't have taps. You would go to the well and, pump on the well, and out would come your drinking water. And what did he notice? He looked at these dots and he said, hey, these dots seem to be concentrated around something. What are they concentrated around? That X is the source of where the water pump was. And he noticed that basically, as the prevalence of cholera increased the closer you were to this water pump. And all that they did, and if out here, if you lived out here, if you lived over here or over here, you probably got your water from there instead of that pump. Basically, by taking the handle off of this pump, okay, and closing that well for a while, he ended the epidemic. And he kind of proved that the source of cholera was drinking water. Okay? Any questions about that? And to discover that basically was a data map. Any questions? I think it's inspiring. Here is an example from Tufte's book of the difference between a good and bad visualization that I like. Now, when I was in graduate school, the Space Shuttle Challenger lifted off and blew up, a minute into its flight. It was a terrible disaster, and everyone wanted to try to figure out what had caused it. Now, it turns out that right before launching the rocket, the engineers were desperate, trying to tell management. They said, we have these rockets have these sealant rings, okay? And if you launch it when it's cold, it looks like there's data, that the sealant rings achieve more, have more damage on the missions when it was cold. And they said, look at this. This shows all the sealant rings, okay, when, every mission, okay, there were 2 of these rocket boosters per flight, okay. This shows us for every mission how much damage there was. And as you can see by looking at this, we get a lot more damage when it's cold. And management looked at this figure and said, you guys are eggheads. I don't see anything. Okay? Here on the right is a redrawing of this data. Okay? That is the data on here. Okay? Which is showing what? There is a dot for every mission and the temperature it was when it got launched. Okay, so the x-axis here is the temperature at launch. The y-axis is the amount of damage. Okay, and the fit line that he's having here, he has this tentative fit line that is showing you, how much damage there was as a function of temperature. They're saying, look, we didn't launch too many missions when it was cold enough, when it was, so far we haven't launched that many missions. We haven't launched any missions when it was below 50 degrees. But if you look at this thing, it looks like the amount of damage we're getting to this critical component is growing rapidly as the temperature drops. When you launch tomorrow, this is where the temperature is going to be. And we think if our model is right, you're going to have a terrible disaster. Okay? If you plot the data in this way, to me it is obvious that what the engineers are trying to say that they're fearful of. Whereas with this visualization, okay, there's not a message that stands out. Okay, I don't know if people are understanding what I'm saying here. But this to me is to me, this kind of captures what the story was in a way that should have convinced management. And sure enough, they launched it. It was 29 degrees and the rocket blew up. Okay? Any questions about that? Okay. So these I find inspiring. Here's another one that I find inspiring related to the question that we talked about today. How did we show in a presidential election not only who was winning each state, but by how much are they winning each state? This is supposed to show you we're having an election to decide who is going to win the election. Is it going to be Biden or Trump? And this is showing the state of the election not too far before the actual vote. What is this showing? They sorted the states according to winning margin most Democratic to least to most Republican, right? So they sorted them based on redness and blueness. As you'll notice, the colors are getting paler in the middle because that's exactly what you would expect. If it's most red here and most blue here, the most even states are going to be in the middle. What is the important thing? He had the width of each bar here is going to be the number of electoral votes it gets. So California has a big bar. New Mexico has a small bar. And what is he showing you? The winner of the election was going to be the guy that got one more than half the electoral votes. So what is the color? Who's winning the election? Biden is winning the election. Because right now at the splitting point, the state that he needs, the state that decides, would decide the majority is a blue state. What does it show us? It shows us, what other states are in play. If Biden is going to win, if Biden loses Pennsylvania, okay? If Biden lost Pennsylvania and lost these other states, he would lose the election. That's what this is telling you, okay? As it turns out, what happened in the election? Well, Ohio went red. Georgia went blue, I guess, if I remember correctly. North Carolina went red. But Pennsylvania and Florida went red, even though it was there. Okay? But because Biden captured all the states that were labeled blue and held Pennsylvania, that was why he won the election. Any questions about it? Yeah.
Angle.
What is the meaning of the angle? Well, the problem is, let's think about what this graphic is doing. What I like about it is, again, it's showing an inherently one-dimensional thing. Redness or blueness is a one-dimensional thing. You could draw it as a single bar, but then there's very little space devoted. You have to find a way to put the two-dimensional bar, the one-dimensional bar in a two-dimensional plot in order to make sure you have enough area for it. Now, the artist there decided to tilt it rather than have it be straight. Why did they tilt it instead of having it be straight? My guess is the thing that's most important, okay, is the area right around here. Because those are the states that are deciding it, right? No one cared how Massachusetts voted or Oklahoma, because those were known way in advance. But the real critical thing was what were the states that were on the boundary. And by tilting the line, you increase the area where the boundary is. Does everybody kind of see it? If you had the line horizontal, Notice that by tilting it, the line gets longer. You're showing more area around the states that are debating. That's why I guess he tilted these things. Okay? We can decide whether we like that or not. I kind of like this visualization. Any questions? Okay, what else do I say? Any other ones? Let me just show you some terrible visualizations that students have given me over the years. And just to make sure that you don't do these kind of things. Here was a plot of word frequency as a function of the most popular word to the least popular word. This measures the frequency, is the y-axis is frequency, the x-axis is the relative rank of that word in popularity. How would we improve this plot? Changing the scale in what way? You can use logarithms. I think yes, if you plot it in a log-log way, that actually is the way that you would show this thing. That was power law behavior, right? When you showed it on a log scale, you now got to see what the other points were doing. This is where you had a log of frequency versus the real rank. If you do a log-log plot, you get a straight line, and that's kind of revealing of a power law. But if we ever have a world where most of the area is dominated by very few of the points, then you probably need a nonlinear scaling of the axis in order to show what's going on. Any questions? Here was a graph that one of my students constructed where they were trying to plot what was the mean energy, okay, of a gene. You don't need to know what this thing is, but what do you need to know about genes? Genes have energies according to the structural energies. And this is a measure of how much energy was there at each position of the gene. So you could imagine that a gene has a length of 300. You could plot the energy at any given point. This is showing the average energy at any given point in the gene. Right? Took all the genes and it plotted and showed the average energy at every position. And what does this plot say? Does anyone have an interpretation of what that plot is saying? You're saying, my God, something amazing is happening here. Okay? Is that what you're kind of saying? Look, there's suddenly tremendous fluctuations. Here the energy gets really negative. Is that what the important message of this experiment is? Certainly looks like it from the plot. But what's the truth? If we plot a cumulative distribution of the number of genes of length such and such, okay, what do we see? There are a lot of genes that are short. This many genes are all less than 200. This is less than 100. What happens by the time we get to 1,000? Very, very few genes are of length 1,000. Okay? Most genes are relatively short. Okay? So what is this plot showing us, really? This is showing us the average energy at positions. Why is this thing jiggling and doing this?
Small number of genes make the same effect as the others.
So small number of genes means the weirdness of any one gene is going to be visible here, where all of that is going to be captured on. All that this is showing us is the variance that happens when you have a small sample. Okay? If I sample one person and say what their weight is, it could be very high, it could be very low. When I average a lot of things, okay, it becomes smooth, right? The problem here was that they were not enough, you're averaging things and the variance that you're seeing, the jumping up and down, is not reflecting that something special is happening with the biology. It's reflecting the fact that you have no data, okay? And that's just noise. Any questions about that? A lot of times people are proudly voting things, they see things jumping around, they think it's a signal. All it is normal variance. Any questions? Okay, and yes.
What should we do about?
What should you do about this small sample? What would be the way of dealing with it? I can think of two different ways you could deal with this. Okay, does anybody have a proposal? One possibility is to drop it. Says I don't have enough data after this. Let's delete that from the graph. That would be one way to do it. What would be another way to do it?
Wait.
What?
Wait. Because of the number of things, we can assign a weight each.
Saying assign a weight, I would say that having a different number of bins would probably be good, right? What if we said now that instead of each one of these being an individual length, actually, there are less points if you look at it. This is 500. We did some binning. What if I had instead binned all the samples from here to here? Then I would have gotten 1 point and it probably would have been right. What if I binned all the samples from here to here? I would have gotten 1 point and it would have been right. What if I binned all these samples? I would have gotten 1 point, right? If I had done a histogram where I had the same number of items in each bin, I would then have not had this variance. That's the way that I would have, that would have been probably a better way to do it. Would be to have each histogram, there'd be a range on it. I should have fewer points out when the data got sparse and clump them together. And that would have shown the right thing. Any questions? Okay, any questions on visualization? Okay, I'm going to stop here on the visualization part. Some of the other slides have amusing examples of good and bad, of bad graphics that perhaps you'll want to look at sometime. But what I'd like to do is just quickly, first of all, ask, are there any questions now about the homework? Either the homework, any observations about the homework people want to talk about? Let's have a quick discussion about the homework. Anything people want to talk about? Okay, anything people want to talk about on the project proposals? Okay, this is your chance now. Okay, again, what I want is every group by Thursday, hopefully you will submit your 3 to 5 page, and 3 is fine, proposal on which is the project you've done, you want to show what you want to do. Make sure the main thing you want to convey is that what it is you think you want to do. You want to show that you've done enough preliminary stuff to convince us that you can do it, that you have access to the data, that you know what your plan is. This is kind of it. We're not going to hold you to it. But I want to be able to read this, and I want you to know what you're going to do next when it comes time to actually work on this more. Any questions about the project proposals? Any questions
Claude,
about any of the individual projects? Okay, I'm seeing there was some comment on, there may have been some comment ups on chat, which I haven't been seeing. Okay, okay, is it possible to extend the due date? The answer is no. Okay, and the reason for this is very clear. This is a proposal. A proposal, does that mean that you finished your project when you turn this in? No, it means that you're going to start your project. You can't finish your project till you start it. And the goal here is make sure that I want to know what you're going to be working on. Okay, I want you to know what you're going to be working on. And that it's important that we settle this at this point in the semester. So unfortunately, I cannot extend the due date of this. Any questions? Any other questions about the proposal or any of the underlying projects? Okay. It's not, I'm gonna go move on to something different. So I'm gonna give you guys one more chance here. Okay, hold on. Any other questions about the project? Some topics will be provided. Is it okay to use additional data found online? Finding using additional data found online is absolutely fabulous. Okay, so that's the kind of thing that we would like to do. By no means do I think we described all the data that you can use. The goal here is you have a question you're trying to answer or something you're trying to do. If you can find your own data that's better or more interesting or something like that, that I think is a fabulous thing. Okay, my hope was actually that we didn't provide so much data to people that they're not going to have to do some kind of looking or some kind of thinking or some kind of preparation on it. But yes. Any other questions about any of the projects? Okay, going once, going twice. Okay. Okay, what I would like to transition into is our next subject, now that we finish with visualization, is some stuff related to building and evaluating models. We talked earlier about we've talked about a bunch of things in data science. We've talked about the idea that we want to ask questions. We've talked about a reason that we need to get data. We've talked about the need that we want to do some level of exploratory data analysis to see what's there, to look at the distributions, to clean it, to stuff like that. We've talked about visualization, okay, which is how do you communicate the final aspects of what you have learned, okay? But the remaining kind of chunk that's probably going to be the bulk of what we're going to talk about overall for the rest of the semester is building models of it. Modeling is the idea of taking what we learn and building predictions from it. Okay? You guys have had to do that on your homeworks by using things like linear regression and stuff like that. But again, when you're building models, the goal is to try to make forecasts or predictions for stuff that, examples in the data that we haven't seen yet. And the key steps that we'll be talking about are how do you build a model, how do you fit it, okay, set the parameters for that particular model, and how do you validate it. Now, the first observation is that for any given data set, there are many, many different models that are possible from it. This is a cartoon that I kind of like, which shows the possible fits that you can have for a particular data set. Okay? You could do a linear fit, like linear regression. You could do a nonlinear fit like quadratic or a logarithmic thing or an exponential. Okay? There are fancier methods that we're not going to talk about, like LOS or logistic things. You can connect everything by just make it like it was a plot, okay, where you connect it by polylines. You can fit it by a high degree polynomial. Typically, there's many, many ways that you can fit a particular data set. Which one is the best fit? Okay, that's actually, I guess, the question that we want to take a look at here. And the answer is, as with everything else in this class, is it probably that it depends. Okay, there are different criteria by which you're going to judge how good a fit is. This fit, if you look at taking the points and connecting them by lines, this perfectly fits the data. Does everybody agree? Okay. Now, I also think this is a terrible model. Something like this, a linear fit, does not perfectly fit the data. Okay? But I'm probably more likely to believe a prediction made by the linear model than this potentially overfit model. So we need a language to talk about whether models are good or bad. Okay, and that is what I'd like us to talk about. And maybe this is where I'm going to end. Okay, so next class we're going to start to talk about philosophies of modeling and how do you evaluate models. Okay, as kind of our gradual introduction into things like machine learning. Okay, any questions about other projects? Okay. Any last, I've still got 3 minutes. I'm not going to force you to stay here, but any other questions about projects? Okay. If not, good luck on it. I'm going to my office for office hours now. I will turn on the television if you guys want to talk about your particular project. Okay, and if not, good luck, and I'll see you guys next class. Okay, bye-bye.